For the first time in human history, a telescope has captured a real, undeniable image of a planet orbiting another star, a world that should not exist where it is sitting, and what it found afterward is even stranger. So stick around and hit subscribe right now because tonight we are walking through every single discovery this triggered. This is not some distant abstract announcement buried in a scientific journal either. This genuinely changes how we think about our place in the universe. And by the time we finish walking through everything Webb has already found, you will understand exactly why. So many astronomers around the world are already describing this particular stretch of discoveries as the single most important chapter in the entire history of exoplanet science so far. For years, astronomers have genuinely dreamed of seeing another world the exact same way we see our own, clearly, directly, undeniably real. Not a blurred signal, not some distant shadow, not a simulation carefully stitched together out of raw data, but an actual image of a planet orbiting another star, a world with its own sky, its own atmosphere, its own unfolding story. And now, for the very first time in human history, the James Webb Space Telescope has done exactly that. It captured the first genuinely real image of another world, a world that should not exist where it currently sits, a world stranger than almost anything scientists had imagined, and a world that is already rewriting the established rules of planetary science. Before Webb, capturing a genuine direct image of a planet orbiting another star was considered one of the single hardest technical challenges in all of modern astronomy. Since the overwhelming glare pouring out of any host star typically drowns out the incredibly faint light reflecting off a nearby orbiting planet, the way a single candle sitting right next to a lighthouse would become essentially impossible to spot from any real distance. Overcoming that particular challenge required an entirely new generation of instrument design, precise starlight blocking technology, and mirror sensitivity considerably beyond anything previous telescopes had ever managed to achieve. Webb's enormous mirror, combined with its specialized coronagraph instruments designed specifically to block out overwhelming starlight, finally made this decades-old dream achievable in practice rather than remaining purely theoretical. And the fact that it succeeded on essentially its first serious attempt says a great deal about just how carefully engineered this particular telescope genuinely turned out to be. That single image alone, years in the making, took an enormous amount of careful engineering just to properly separate a faint planetary glow from the overwhelming brilliance of its parent star. But this particular image turned out to be only the beginning, because as Webb kept observing further, it uncovered something even more shocking still. Other planets carrying impossible chemistry, mysterious atmospheres, broken rules of formation, and one world that may even hold the strongest hints of alien life we have ever detected anywhere. Tonight we're going to step directly into that first historic image and carefully follow the entire trail of discoveries it ended up unleashing across the wider scientific community. K218b was never actually meant to become the center of a global scientific debate. At first, it was simply treated as just another distant super-Earth, too large, too far away, and too difficult to properly study with the instruments available at the time. But once Webb finally pointed toward it, the telescope did not simply collect ordinary data. It effectively peeled back the planet's entire atmosphere, layer by layer, molecule by molecule. The James Webb Telescope revealed a world wrapped inside a genuinely dense envelope of hydrogen, beneath which may lie something truly extraordinary. A global ocean deep enough to comfortably swallow entire mountains whole. Water vapor showed up almost immediately, strong and completely unmistakable. But what came next is what pushed this particular planet directly into scientific history. Webb detected methane, then carbon dioxide, and then the one specific molecule that sent genuine shock waves rippling through every major observatory on Earth, dimethyl sulfide, a chemical that here on Earth originates almost exclusively from living organisms inside our own oceans. This was not simple background noise. It was not instrument distortion either. It repeated consistently across multiple separate observations. Suddenly, the idea of a dark, endless alien ocean stopped sounding purely fictional. It started sounding genuinely probable instead. A world where sunlight filters weakly through a thick surrounding atmosphere, gently warming the boundary between day and night into a stable, potentially habitable twilight zone. A world where life, if it genuinely exists there, could rise slowly and silently, gradually forming ecosystems unlike anything found here on Earth, yet still governed underneath by that exact same universal chemistry shared across the cosmos. Scientists genuinely did not want to say it out loud at first, but they eventually had to admit it plainly. If any single planet we have ever studied could realistically host life, K218b may well be the very first genuine contender. Researchers have been careful, almost painfully careful, to avoid overstating this particular finding. Since dimethyl sulfide could theoretically form through chemical pathways, we simply have not identified yet pathways that have nothing whatsoever to do with living organisms. But every single time researchers have tried to explain this specific signal away using purely non-biological chemistry, the proposed explanations have required increasingly exotic, increasingly unlikely combinations of conditions, conditions that would themselves represent genuinely strange discoveries in their own right. Some proposed alternative explanations have invoked unusual mineral chemistry involving trace metals we do not typically expect to find in that particular combination, while others have suggested exotic volcanic processes entirely unlike anything documented here on Earth. And each new alternative explanation researchers put forward ends up sounding more contrived and less likely than the simple, straightforward biological explanation it was originally meant to replace. At some point, when the simplest explanation for a signal keeps stubbornly pointing toward biology, and every alternative explanation keeps growing more complicated and more implausible instead, scientists have to seriously start taking that simplest explanation seriously, even while publicly maintaining the appropriate caution that comes with any claim this significant. When Webb captured the first real image of HIPS 65426b, astronomers fully expected to find a fairly typical gas giant, massive, distant, and entirely predictable in every way. But the resulting image revealed something considerably stranger instead. HIPP 65426b is a colossal planet weighing in at nearly 7 times the mass of Jupiter, orbiting so incredibly far from its own host star that it genuinely should not exist at all, according to our current understanding. Based on essentially every planetary formation model we currently have, giant planets this massive must grow directly inside the swirling disk of dust and gas surrounding a genuinely young star. But this particular world sits far beyond that entire formation region, sitting alone out in the darkness, almost as though it had formed somewhere completely different entirely, and simply arrived at its current position much later on. That kind of positioning genuinely breaks the standard playbook astronomers have relied on for decades, since the whole traditional model of planetary formation depends heavily on a young star's surrounding disk having enough raw material concentrated closely enough together to actually build something this massive within a reasonable time frame. Out at the extreme distance where HIP 65426b currently sits, that surrounding disk would have been far too thin and far too spread out to plausibly assemble a planet anywhere close to 7 times the mass of Jupiter through any conventional gradual accretion process alone. Some researchers have started wondering whether we simply need to expand our entire mental picture of what counts as a normal planetary system in the first place, since our own solar system, with its neatly ordered arrangement of rocky inner worlds followed by gas giants further out, may represent just one narrow example drawn from a far wider, far messier range of possible outcomes scattered across the galaxy, rather than serving as the universal template every other system is quietly expected to follow. The underlying mystery deepened even further once the James Webb Telescope carefully analyzed its light signature. Rather than the smooth, predictable atmospheric profile you would normally expect from an ordinary gas giant, HIPP 65426b displayed unexpected chemical layering, strange temperature variations, and cloud structures that genuinely defied basic atmospheric stability. The atmosphere did not behave like a planet peacefully evolving inside a calm, stable orbit around its star. It behaved instead like something genuinely unsettled, something that had clearly experienced violent changes at some point, or had perhaps traveled across multiple different environments entirely before finally reaching its current resting position. This eventually led scientists to propose theories that would have once seemed genuinely unthinkable. Perhaps this particular planet was violently ejected from an entirely different star system during some chaotic ancient collision and was later captured by its current host star instead. Or perhaps it originally formed alone out in the cold darkness of true interstellar space, functioning as a rogue planet, wandering freely for millions of years until gravity finally claimed it and pulled it into orbit. But the single most intriguing possibility remains the one astronomers tend to whisper about far more than they openly admit, that HIPP 65426b is not simply some isolated anomaly at all. It represents a genuine clue, a clear sign that entire solar systems may actually form through processes we have never properly imagined before, that planets can realistically migrate across genuinely enormous distances over time, and that the wider universe is fully capable of assembling complete worlds through mechanisms we have not even really begun to properly understand yet. Some researchers have even started referring to planets like this one as orphan giants, worlds that essentially lost their original family of stars entirely and were later adopted by a completely different star system altogether. A genuinely strange kind of cosmic foster care playing out silently across enormous interstellar distances. If that particular explanation holds up under further scrutiny, it would mean our galaxy is quietly full of wandering giant planets drifting between star systems, occasionally getting captured and settling into new orbits that make absolutely no sense according to how we currently believe planets are supposed to form in the first place. That alone would force a genuine rethink of how common these kinds of dramatic planetary migrations actually are across the wider galaxy, rather than treating them as some kind of rare, isolated exception. Webb's first real portrait of an exoplanet was never simply proof that other worlds genuinely exist out there somewhere. It was really a much larger message. These worlds are considerably stranger than anything we had originally expected. And the discoveries that followed afterward would go on to push that underlying mystery even further. Still, Proxima b has been widely described as the single most tempting planet anywhere in the entire galaxy. Sitting at just over 4 light-years away, it orbits directly inside the habitable zone of Proxima Centauri, the closest known star to our own Sun. From the very moment it was originally discovered, astronomers immediately began imagining oceans, atmospheres, and quite possibly even the faint outlines of continents hidden beneath alien cloud cover somewhere on its surface. It genuinely represented everything we had hoped to eventually find in a nearby exoplanet. Close, rocky, and sitting comfortably inside the perfect temperature range needed to support liquid water. But when the James Webb Telescope finally turned its powerful gaze toward this particular nearby world, the initial excitement quickly turned into genuine frustration instead. Proxima b orbits far too close to its own host star. So close, in fact, that the planet effectively disappears entirely into the surrounding glare, making its atmosphere essentially impossible to observe directly using current instruments. The James Webb Telescope simply cannot separate the faint light reflected off the planet's surface from the far more violent radiation constantly pouring out of its parent star, leaving us with a world we can technically detect through gravitational and orbital measurements alone, but genuinely cannot properly see in any real meaningful detail. And then an even deeper underlying problem emerged on top of that. Proxima Centauri is not a genuinely calm, stable star by any means. It happens to be a red dwarf star that is particularly prone to massive solar flares. Sudden bursts of radiation so intense they could realistically strip an entire planet's atmosphere away within what amounts to a mere geological heartbeat. If Proxima b once genuinely had oceans or any kind of breathable sky at all, they may well have already been blasted completely away a very long time ago. Or perhaps even worse, the planet could instead be permanently locked in a fixed, unchanging position relative to its star, with one entire side left permanently scorched under constant sunlight, while the opposite side remains permanently frozen in darkness, clinging to any real chance of habitability, only within a narrow, thin band caught between perpetual day and perpetual night. This particular paradox is exactly what makes Proxima b one of the single most haunting discoveries Webb has ever revisited during its ongoing mission. It represents the closest world to us, the very planet we openly dream about someday visiting, the natural first destination for any future interstellar mission humanity might eventually attempt. And yet, it may remain permanently beyond our reach, and permanently beyond our full understanding for a very long time to come. Engineers and mission planners working on future space telescope concepts have specifically cited Proxima b as one of the primary reasons for developing entirely new instrument technology capable of physically blocking out a star's overwhelming glare with far greater precision than anything currently available. Without that kind of dramatic technological leap forward, Proxima b may simply remain a tantalizing, frustrating mystery sitting right on our cosmic doorstep. Close enough to dream about visiting someday, yet still stubbornly too bright and too close to its own star for us to properly study, using anything we currently have available in our toolkit. In the meantime, researchers continue squeezing every last bit of usable information out of the limited data we already have, carefully modeling how a red dwarf star's violent flare activity would realistically interact with different hypothetical atmosphere types, trying to at least narrow down the range of plausible scenarios, even while direct observation remains firmly out of reach for the time being. We can technically detect its presence, measure its gravitational pull, and sense its rough surface temperature. But its deeper mysteries remain fully concealed behind the blinding fury constantly radiating off its own host star. Proxima b genuinely reminds us of something humbling, that even the very nearest alien worlds can remain almost completely hidden from us, and that sometimes the planets most genuinely full of life are not necessarily the ones sitting closest to our own home. When James Webb observed WASP 39b, astronomers fully expected to find the usual predictable profile of a hot Jupiter, a massive gas giant sitting so close to its host star that its atmosphere ends up stretched thin and constantly boiling away. But instead of finding simple, straightforward predictability, Webb instead uncovered one of the single most complex atmospheric signatures ever properly recorded anywhere. Its surrounding skies contain water vapor, sodium, potassium, carbon monoxide, methane, and even sulfur dioxide, a specific molecule that forms only through chemical reactions directly triggered by intense stellar radiation. This particular finding was genuinely shocking because these exact kinds of chemical reactions had previously only ever been purely theoretical in nature. No telescope had ever actually witnessed them happening in real time on another world before. Webb had effectively captured the very first solid evidence of active photochemistry occurring inside an alien atmosphere. Chemical processes essentially identical to the ones responsible for shaping Earth's own protective ozone layer, except occurring instead on a planet considerably hotter than a working furnace. Even stranger still, the precise ratios between all of these different molecules did not properly match any existing scientific model. WASP 39b's atmosphere effectively behaves like an entire laboratory, full of alien chemistry, packed with chemical reactions we do not yet fully understand, and underlying patterns we genuinely cannot yet properly explain. Researchers working on this particular data set have described the experience almost like discovering an entirely new branch of chemistry playing out in real time. One governed by the same fundamental physical laws we already know, but expressed under conditions so extreme and so unfamiliar that predicting the exact outcome in advance turned out to be considerably harder than anyone initially expected going in. Every fresh detail extracted from WASP-39b's spectrum has forced modelers back to their equations, adjusting assumptions that had gone essentially untested for years simply because no instrument before Webb had ever been sensitive enough to actually check them properly against real data. This particular discovery ended up changing quite a lot. It proved conclusively that even the most extreme hostile worlds imaginable can still host genuinely complex, actively evolving atmospheres, and that the underlying chemistry of the wider cosmos is considerably richer and considerably more unpredictable than we had ever previously imagined. Photochemistry like this matters enormously beyond just this one particular planet, too, because the exact same basic chemical processes responsible for building Earth's protective ozone layer over billions of years appear to be actively at work on a completely different kind of world entirely. One far hotter and far more extreme than anything we experience here at home. That tells researchers these particular chemical pathways are not some rare, delicate accident unique to Earth-specific conditions. They represent a more universal, more robust process capable of playing out successfully across a genuinely wide range of different planetary environments, which meaningfully broadens the overall range of worlds worth searching closely for similarly complex atmospheric chemistry going forward. That is a genuinely significant shift in how astronomers approach the wider search for interesting atmospheres, since it means even planets that look inhospitably extreme at first glance might still turn out to be genuinely rich, chemically active places worth studying closely, rather than simply written off as uninteresting furnaces not worth the telescope time. For years, the TRAPPIST-1 system was widely considered the single crown jewel of exoplanet discoveries, an entire system containing 7 Earth-sized worlds, several of them orbiting comfortably right inside the habitable zone. It represented the closest thing we had ever found anywhere to a genuine miniature version of our own solar system. And plenty of researchers genuinely believed at least one of its planets would eventually reveal clear signs of life once Webb finally got the chance to examine them properly. But once the telescope finally analyzed the first 2 worlds in that system, the resulting findings turned out to be genuinely devastating. There was simply no atmosphere at all present on either planet. Not a thin, wispy layer, not even a faint trace, not the slightest whisper of any gas clinging to their bare surfaces whatsoever. Just completely exposed bare rock, constantly bombarded by violent radiation streaming out from their host ultra-cool dwarf star. Without any surrounding atmosphere at all, these particular planets simply cannot retain heat properly, cannot shield themselves from harmful radiation, and cannot sustain any of the basic underlying chemistry genuinely required to support life in any meaningful form. It is genuinely worth remembering just how much anticipation had built up around this particular system in the years leading up to Webb's launch. With entire conference sessions, popular science documentaries, and countless magazine covers speculating about what kind of life might be quietly waiting on one of those 7 worlds, the initial dreams surrounding TRAPPIST-1 faded away almost instantly following that discovery. A system once widely regarded as a genuine galactic oasis instead revealed itself to be little more than a chain of completely sterile, lifeless worlds. And yet, this particular disappointment ultimately became one of James Webb's single most important lessons for the entire scientific community. Genuine habitability turns out to be far rarer than we had originally imagined. And even a system that looks genuinely perfect from a distance can end up hiding a considerably harsher and more lifeless reality underneath once you actually look closely enough. Researchers have not entirely given up on the remaining TRAPPIST-1 worlds sitting further out from the host star, though since those particular planets received noticeably less intense radiation overall. And at least a couple of them could theoretically still be holding on to thinner atmospheres that Webb has not yet had the chance to properly examine in full detail. But the two inner worlds already studied have genuinely tempered expectations considerably across the entire astronomical community, serving as a sobering reminder that an ultra-cool dwarf star's relentless radiation output can strip away a planet's atmosphere long before life would ever even get a realistic chance to properly take hold there in the first place. That distinction matters considerably for how future missions get planned and funded too, since it suggests researchers should weight their search efforts more carefully towards star types that flare less violently overall, rather than simply chasing every rocky planet sitting inside a technically defined habitable zone, regardless of how hostile the surrounding stellar environment actually turns out to be up close. As James Webb continued steadily surveying distant star systems one after another, one particular underlying truth became genuinely impossible to keep ignoring. The wider galaxy is absolutely overflowing with planets. Big ones, small ones, frozen ones, scorched ones, entire oceans worth of distinct worlds scattered randomly across every single arm of the Milky Way. And yet, despite all of this sheer abundance, not one of them has actually revealed any clear, undeniable sign of genuine biological life. So far, we consistently find atmospheres, storms, oceans, complex chemistry, and even specific conditions that closely resemble early Earth, but still no confirmed signal of actual life anywhere. This particular contrast remains genuinely unsettling to sit with. Statistically speaking, life really should be everywhere out there. But purely from an observational standpoint, the universe remains stubbornly silent on the matter. Either genuine life is incredibly rare throughout the cosmos, potentially hiding in forms we simply do not yet properly understand or know how to detect, or the wider universe is considerably more selective about where it actually allows life to take hold than we had ever previously imagined. There's a third possibility, too. One researchers take just as seriously as the other two, that our current instruments, however impressive they already are, still simply are not sensitive enough yet to catch the specific faint biological signals we would actually need to see. Meaning the silence we are currently hearing may say considerably more about the limits of our own technology than it says about the actual presence or absence of life scattered across the galaxy. Webb's ongoing discoveries genuinely remind us that simply having all the right basic ingredients present does not automatically guarantee that life will actually emerge. Plenty of planets studied so far seem almost habitable, almost genuinely Earth-like, almost comfortably familiar in many ways, yet still consistently fall just short in some critical way. And with every single new world we carefully examine, this underlying paradox only continues growing deeper still. The universe appears to be absolutely full of places where life genuinely could plausibly exist, yet apparently none where it undeniably actually does, at least not according to anything we have confirmed so far. Some scientists have started calling this the Great Silence Paradox. Since every individual ingredient life supposedly requires keeps showing up scattered across the galaxy in genuinely staggering abundance: water, organic molecules, stable temperature zones, rocky surfaces, and yet the actual confirmed spark of biology itself remains stubbornly absent from every single world we have managed to study closely enough so far. It raises an uncomfortable possibility that researchers are only now beginning to seriously grapple with, that the actual leap from simple chemistry to genuine self-sustaining biology might be a far rarer, far more improbable event than anyone previously assumed, even when every other necessary condition appears to be lined up perfectly in a planet's favor. It also raises an equally interesting flip side worth considering, that Earth itself might represent something closer to a genuine statistical outlier rather than a typical expected outcome of ordinary planetary evolution. Meaning the specific sequence of events that allowed life to take hold here billions of years ago may have depended on a chain of fortunate coincidences considerably longer and considerably more fragile than we ever previously appreciated. If that turns out to be true, it would not necessarily mean life is impossible elsewhere. Simply that Earth's own particular success story might be far harder to replicate than the sheer abundance of seemingly promising worlds out there would initially suggest. All of James Webb's discoveries taken together point directly toward one profound underlying truth. The universe is considerably stranger, considerably richer, and considerably more unpredictable than we had ever previously imagined it to be. We have now personally witnessed oceans wrapped inside dense hydrogen skies, giant worlds drifting through space in places where established physics genuinely says they simply should not exist at all. Nearby planets permanently hiding behind the blinding fury of their own host stars in entire atmospheres so genuinely complex, they effectively rewrite our existing rules of chemistry from scratch. We have personally watched our single greatest hopes like the TRAPPIST-1 system quietly crumble apart under the harsh, unforgiving clarity of real hard scientific data. And we have personally witnessed the deeply unsettling silence coming from an entire galaxy, overflowing with countless planets, yet still offering absolutely no clear, confirmed sign of actual life anywhere within it. But for the very first time in all of human history, we are no longer simply imagining these distant worlds from a comfortable distance. We are now actually seeing them directly with our own eyes. Webb has genuinely opened up an entirely new window under the wider cosmos, revealing these distant planets not merely as abstract theories or faint distant signals buried in noise, but as real physical places with real atmospheres and real unfolding stories quietly written directly into their own captured light. But think about what that actually represents for a moment. Every single photon Webb captures from one of these distant worlds has traveled an almost unimaginable distance across the emptiness of space, carrying within it a faint, precise chemical fingerprint of exactly what the planet's atmosphere is actually made of. We are not merely speculating about these worlds anymore based on rough calculations and educated guesswork. We are reading their actual composition directly, molecule by molecule, the same way a chemist might analyze a sample sitting right on a laboratory bench, except the sample in question happens to be sitting many trillions of kilometers away, orbiting a star we will likely never visit in person. There is something genuinely humbling in that realization, too. The idea that a machine sitting quietly a million miles from Earth can now read the chemical fingerprint of a world so distant that its own light left the surface long before most of us were even born. And by the time that light finally reaches Webb's mirror, it carries within it an honest, unfiltered snapshot of conditions on a planet. We will likely spend our entire lives only ever knowing through data rather than direct experience. Each and every new discovery brings us meaningfully closer to finally answering the single oldest question humanity has ever genuinely asked of the universe. Are we truly alone out here? And if these remarkable new worlds we keep uncovering are any real indication at all, the honest answer may well be quietly waiting for us just beyond the very next star we happen to look at. What Webb has already shown us so far genuinely represents only the very beginning of this much larger story. The next captured image, the next detailed spectrum, the next completely unexpected signal, any single one of them could realistically end up reshaping our entire understanding of the universe forever, virtually overnight. If you genuinely want to follow along with every new discovery, every strange, newly found world, and every fresh breakthrough that brings us meaningfully closer to finally finding real life somewhere beyond Earth, make absolutely sure to subscribe to this channel right now. Turn on notifications so you never miss an update and join us as we continue exploring this vast universe together, one single planet at a time. We genuinely appreciate every one of you who takes the time to sit through these deep dives with us because understanding what Webb is actually finding out there requires a lot more than simply glancing at a flashy headline for a few seconds before scrolling past it. It requires walking carefully through what each individual molecule detected actually means, what each strange orbit or unexpected temperature reading genuinely implies about a planet's entire history, and why scientists react so differently to some discoveries compared to others, even when the underlying headlines might sound roughly similar on the surface. That is exactly the kind of careful, patient depth we plan to keep bringing you with every single future update. As Webb continues its ongoing mission and inevitably turns up even more worlds that challenge everything we currently think we already know about how planets form, how atmospheres evolve over time, and where exactly, if anywhere at all, life might be quietly waiting for us to finally find,